Okay, good afternoon, everyone. Welcome to the Katanov seminar. Today, we're very glad to have Chong Wang from Parameter Institute giving us the talk. So Chong obtained his PhD from MIT, working with Centil, and then he moved to Harvard as a junior fellow. Now he is a faculty at the Parameter Institute from Canada. So his main research interests are topological phases of matters and strongly correlated systems, etc. So today he will be telling us a theory of deconfined pseudo-criticality. So Chong, please.
Yeah, thanks, Lemmy, for the invitation, and thanks for coming. Let me share my slides. Am I doing it right? You can see it, right? Yeah, okay. Yeah, so so I'll be talking about a work done, with my student Maro Chen at Perimeter, and there was another independent work from Adam Nahum that we posted on the same day. It's essentially the same story. Okay, so by the way, for this talk, maybe most of the first half will be on background information, like background stuff. I don't expect all of you to know that, but I noticed several experts in the audience that I didn't really expect you to be there. So you can sleep through the first half, doesn't really matter. Okay, so the deconfined criticality, at least the canonical one, is an example of quantum phase transition primarily in the setting of quantum magnetism that's beyond the Landau paradigm. That's chiefly why we're interested in it. And this particular example, let's look at the two-dimensional square lattice and imagine having, for example, a spin-half moment sitting on each lattice site. And think about some general anti-ferromagnetic interaction. So there are two simple symmetry breaking phase ground states one can imagine. One is the famous Neel anti-ferromagnetic state. So the spins order in the up-down way. The other one is known as the valence-bond-solid order, or sometimes called dimer phase. That is, so this phase doesn't break spin rotation symmetry, unlike the Neel anti-ferromagnet. Rather, I have this spin singlets formed in pairs, right? So each link, each purple link here represents a spin singlet formed by two adjacent spin halves. But this pattern obviously breaks the lattice rotation symmetry, right? So if I rotate the whole thing by 90 degrees, it's a different pattern. So the two phases break very different symmetries. So Neel breaks spin rotation, but not lattice rotation, while the VBS does the opposite. And if you try to describe a phase transition between two such phases within the usual Landau paradigm, what you will find is that the transition is either going to be strongly first order, or you will need some intermediate phase. Right? So it's, within the Landau paradigm, you can't have a direct continuous transition. But it turns out quantum mechanically you can. And that's the story of deconfined criticality. And even from a continuum field theory point of view, this is actually an interesting phase transition. So the continuum field theory description of this transition looks like this. So I won't go into detail of what this really does. It's two scalars coupled to a U1 gauge field. So I won't actually use anything about this Lagrangian for the rest of the talk. So if you're not familiar with the details of this, what's called CP1 gauge theory, it doesn't really matter. Okay? This is really just to show you that a field theory, a well-defined continuum field theory description of this phase transition exists. The only thing I will say is that it's a gauge theory, even though it's well-defined, but the IR dynamics is strongly coupled, and we don't really have a good analytic solution of this theory. So technically, we don't know what's really good happening in the IR. So there are various tools one can use to study this, for example, like large N expansion and so on. But at the end of the day, N equal to 1 or 2. So strictly speaking, we don't really know what's going on. So to really study this phase transition, one needs some numerical simulation. And that has been done extensively over the past 15 years or so.
Can I just ask,
yeah.
with the CPN model in 2+1 dimensions, this model,
Yeah.
is it going to be non-trivial CFT in the infrared? Is that the conjecture?
Yes. So at least that used to be the conjecture. So what we know for sure is if it's CPN at large enough n, then that's a CFT in IR. So that's controlled. But nobody knows what's the critical n, how large n has to be.
Okay, very good. Thank you.
Yeah, sure. So yeah, so for this model, a lot of new, basically lattice Monte-Carlo simulation has been carried out over the past 15 years. And they are on different lattice realizations, so different UV regularization. And they roughly agree with each other. So the consensus is that the transition on all these models do not seem to be first order, do not seem to be discontinuous up to the maximal lattice size people can reach, which is actually quite remarkable. If you look at it, it's something like 600 lattice spacing. Okay? So that is to say, if this is a first transition, this has a almost unreasonably large correlation length. It's larger than 600. Okay? The other thing is at the transition, there is an emergent SO5 symmetry that's been numerically observed. So if you look at the lattice model, there is the SO3 spin rotation symmetry, and there's some C4 lattice rotation, which you can be enlarged to U1. But then the funny thing is, exactly at the critical point, it seems that this three-component Neel vector and this two-component valence-bond-solid operator, they seem to be degenerate. There's a symmetry that emerges at the critical point that can rotate between these two seemingly very different order parameters. Okay? And that's being observed, I think, first in this numerical paper. So this is a plot of the histogram, essentially the probability distribution of the order parameters. You see this.
Sorry, just a naive question.
Yes.
So the U1 symmetry on the Neel side is rotation?
Sorry, the Neel side.
I meant the other side, the VBS side.
Oh yeah, that's just the lattice rotation.
Okay.
So that's a Z4 really. But
so it doesn't commute with translations, for example.
Oh yeah, it doesn't commute with translation. So here I'm neglecting translation. It actually matters, but for this talk, let me neglect it.
But the SO3 is an internal symmetry, right?
Yes. Yes.
And somehow this internal and a spatial symmetry combine into an SO5. Is that the statement?
Yes. So at the continuum field theory level, because if I go take the continuum, then all these continuum fields transform relatively simply under the C4 rotation. So you can basically think of the C4 as a simple Lorentz rotation combined with some internal Z4. And that internal Z4 gets enlarged into a U1, even if you just stare at this Lagrangian.
Okay.
And what's even weirder is that U1 and the SO3 of the spin rotation symmetry combines to an SO5 at the critical point.
Thank you.
Sure. Right. So that weird symmetry has been observed. So usually when you see signatures like this, right, the very large correlation length and an emergent symmetry that at the transition, usually we say there is probably a continuous transition or a RG fixed point there, because otherwise it's hard to make sense of it, right? Especially this emergent symmetry, right? Usually we understand emergent symmetry at a phase transition as there's a fixed point, and even though microscopically I don't have the symmetry, but the terms that break this symmetry are irrelevant at the fixed point. Therefore, you have the emergent symmetry at the critical point. So for all that to work, you need a fixed point to begin with, right? So all this seems to strongly suggest that the transition is continuous. However, it doesn't look at least as like a conventional continuous phase transition. There are two things chiefly. So one is if you actually try to extract the critical exponents at this phase transition, the exponents you get will slightly depend on the system size. So as your system size increases, the exponents keeps drifting. So it looks like as if you actually don't quite reach the fixed point. The other thing is what people have done is to extract the exponents at the largest system size they can get to. Right? But awkwardly, all the exponents extracted violate the bounds provided by conformal bootstrap study. Okay? So the two scaling dimensions, mainly, so one is the correlation length exponent, nu, and numerically, it's been quite consistently measured to be around 0.44. And people have done a very careful job in doing the finite size scaling and so on. But the bootstrap bound is, from conformal bootstrap, what's required is that it has to be larger than 0.51. So there's a clear gap between the two. Also, if you look at the scaling dimension of the order parameter, I mean, in the standard community, it's more often referred to as eta. So that one, numerics has a little bit more discrepancy between different works, but it's roughly around 0.6. But there is a clear bound from conformal bootstrap that requires it to be larger than 0.76. So in both cases, the numerically observed correlation, the scaling dimensions are significantly smaller than the bound provided by the conformal bootstrap. Okay. So which means if you take it to face value, this can't be a real CFT, at least not a unitary one. So okay, so maybe then this transition is a first order one. But then the question is, if it's a first order one, it's a damn weak first order transition. The correlation length is long, and so you even have emergent symmetries that can be observed. So why is the transition so weak? It's such a weakly first order transition, right? A boring answer would be that the lattice models happen to be fine-tuned, but that's very unlikely given that there are several different lattice models that have been simulated. So there is a possible resolution coming from the scenario of, that has several names. One name is the walking coupling constant. So the story goes roughly like this. So we postulate that there is a coupling constant somewhere in the theory. We don't know which yet. That under RG flow, let's say around lambda equal to 0, that roughly looks like this. Right, so there is a quadratic term, lambda square, but then there is a constant piece, epsilon. And the important thing is this epsilon doesn't flow under RG, so it's constant. So if the beta function look like this, well, the RG flow is very simple to work out. So if epsilon is larger than 0, then this is constantly positive. Right? So it never vanishes. So there is no fixed point. The flow goes always all the way from very negative lambda to very positive lambda. Right? So there's no fixed point. And this would be like a first order transition. But if lambda is, but if epsilon is barely positive, that is greater than 0, but still much smaller than 1, then the flow near this lambda equal to 0 region, in this region, will be very slow. It takes a lot of RG steps to actually flow from, let's say, -1 to +1. So if you work out the RG time it takes, which is basically the correlation, the log of the correlation length, then the correlation length looks like this. Right? So then you see that if epsilon is somewhat small, it doesn't even have to be ridiculously small. Just you need something like 0.3 or something. Then this number can already be very large. In fact, this is the kind of form you see in KT transition. And the nice thing about this is that this correlation length can easily be much larger than 1, and there's no fine-tuning required. The only thing you need to postulate is that your UV model or your lattice model starts somewhere at lambda negative. It doesn't have to be exactly -1 or -2, it's just somewhere negative. And that's all you need to have this generically large correlation length.
So would that mean that the continuum model, the CPM model, is just not a good description of the infrared anywhere, or?
Well, not necessarily, right? Because we don't know what was the infrared fate of this. So the infrared fate of this theory could well be something described by this. Right? So there may not be an actual fixed point.
So so what would this constant epsilon correspond to? An effective gap, or
basically, yeah.
Yeah.
Yeah. Well, the gap is the actual gap will be the inverse of this.
Oh yeah, good. Yeah. Good.
Right. So yeah. So it's a first order transition, but it's pretty weak one. Furthermore, when the system is near this lambda equal to around 0, the system essentially looks like a critical point because the RG flow is very slow. It looks almost like the RG flow has stopped. So as long as your system size is much less than this large correlation length, the system looks almost critical. Except, well, lambda is still slowly flowing. So as you gradually increase your system size, even before you reach the actual correlation length, you will see that the critical properties like the scaling dimensions and so on drift slowly as your system size increases. Okay. So this scenario, you can also call it pseudo-critical. It's just another name. So another way to understand all this is to now think about the opposite scenario where you have the same RG equation here, except with epsilon smaller than 0. Then the RG flow is even more familiar. Essentially, you get two fixed points, one attractive, one repulsive. Right? So if you imagine turning epsilon from negative to positive, what happens is these two fixed points gets closer and closer together. Eventually, they annihilate at epsilon equal to 0 and epsilon larger than 0. There's no fixed point anymore. Right? So this is it's called fixed point annihilation. So if you prefer to think about it more formally, you can say that this RG flow still has two fixed points, but no longer on the real axis. So the fixed point values will be lambda at plus minus I square root epsilon. Okay. So you can also call them complex CFTs. So you lose unitarity in a pretty bad way. Everything becomes complex with the imaginary parts, including central charge, scaling dimension, and so on. So one way to say is the pseudo-criticality is eventually controlled by the complex fixed points. So there is actually a fairly old example of this kind of behavior. It's actually in the 2D classical, if you like, 1+1D quantum Potts model. So if I look at the Q-state Potts model in 2D, so it's known that at Q smaller or equal to 4, the transition is continuous. But at Q larger than 4, it's a first order transition. So you can see that even from the exact solutions of some lattice models. However, for Q not too large, let's say 5, 6, 7, the correlation length is known to be pretty large. Especially at 5, the correlation length is 2,000 something. Okay. So if I tell some of my numerical friends today that some of the models they simulate in 2D or 3D quantum models actually have correlation length 2,000, they'll go mentally collapse because there's no way with today's technology that they can reach that scale. But it happens for 5-state Potts model. Okay. So so this is a known phenomenon in Potts model for decades, but the actual theory of this pseudo-criticality has been developed only quite recently, and there it's been worked out. For example, this epsilon in that RG flow equation roughly goes like Q minus 4 divided by pi squared. So you can see that even for Q that's like 7, this number is still pretty small. And numerically, people can, for example, try to observe the drifting behaviors of, for example, 5-state or 6-state Potts model on the lattice. And that has been done. And indeed, what's observed is that it almost looks scaling invariant if I stay below the correlation length, but the observed central charge or scaling dimensions will keep drifting as my system size increases. Okay. All right, so those are some of the motivations to study this pseudo-critical behavior. One can still object by saying this is, at the end of the day, a first-order transition. So why isn't it boring? I mean, after all, even if my correlation length is 2000, a real system will still be much larger than that, if you ever realize one in the lab. Well, one interesting point is that if I study quantum phase transition, things will be slightly different because it's very hard to go to extremely low temperature there. So if I have a quantum phase transition that's pseudo-critical in the sense previously mentioned, then what I will see is that there's a phase transition that's eventually first order, but over a wide temperature range, all the way from a UV scale, let's call it J, to a crossover scale, which is very small. For example, sorry, there should be a minus sign here in the exponent. To a very low crossover temperature. Over all this range, I can see, I can, in principle, observe all the things from quantum criticality. For example, this famous critical fan behavior. Okay. So below that very low crossover scale, it crossover to something less interesting. Okay. So I'm drawing this figure deliberately to make it provocative to some of you, because this kind of diagram you should see quite often if you're working in the strongly correlated electron area. But I'm not making any concrete suggestions, so don't accuse me of. So anyway, back to this deconfined criticality story. So the idea is that if we assume something of this sort happened to the Neel VBS transition, then we can potentially explain those drifting exponents as well as the tension with bootstrap, because there's no unitary CFT anymore. So of course, not agreeing with conformal bootstrap is no longer a real issue. But so that suggestion has been made, I think, first quite long ago in this paper, and subsequently we said a little bit more about this. But there is a question that remains: is can we make the suggestion a little bit more concrete, right? So what is the lambda? Where does that small epsilon, this magical small epsilon in the RG equation come from? Where does it come from? Can we have a theory that incorporates all these features? So this emergent SO5 symmetry, this potentially pseudo-critical behavior, and so on. So that's the goal of the work I'm going to talk about here. Okay. So to talk about the work, let me first introduce you another way to think about, a formulation to think about the deconfined criticality. So I showed you this CP1 gauge theory formulation that describes the continuum limit of the phase transition. So here's another version of that. It's written in a very different way. So it's a sigma model with a Wess-Zumino term. So here, this order parameter n hat is a combination of the 3 Neel vector here and the 2 components of the valence-bond-solid order parameter. So there are in total 5 components. And let me take a normalization so that they live on the 4-dimensional unit sphere. So if I think about the fluctuation of this order parameter, naturally I can write down a nonlinear sigma model with a kinetic term like this. So that's pretty standard. I'm working in 2+1 dimension, space-time dimension, Euclidean if you like. But what's special about deconfined criticality is that there is an additional term, the Wess-Zumino-Witten term. Right? So if you are not familiar with it, it's okay. I don't actually need the exact form of the term here. The thing that I need to emphasize is that this term is possible because of this specific topological relation. Essentially, the pi 4 of S4 is Z. And I want pi 4 here is, let me say 4 is 3 plus 1. So 3 is my space-time dimension. Right? And S4 is the target manifold where my order parameter lives. So essentially, this term measures the winding, the way that this term works is to imagine your space-time to be the boundary of a 4-dimensional bulk. And this term measures the winding number of the winding of the order parameter on this 4-dimensional bulk space-time. And it's known that the coefficient of this term should be quantized. So this k, number k here, has to be an integer. And it's known for quite some time that deconfined criticality can be represented to some degree with using this Wess-Zumino-Witten model at level k equal to 1. I will explain a little bit later, but so let me show you how roughly this works. Right? So there are two regimes one can think about: a weak coupling regime and a strong coupling regime. And the strong coupling regime, sometimes I call it a fantasy regime or cartoon regime. It's harder to say anything precise there. So let me begin with the weak coupling regime, where things are much better defined. Right? So a weak coupling regime, so imagine having a small g, so that the fluctuation of the order parameter is strongly penalized. Then the ground state is basically an ordered phase. What happens is that this n hat gains a non-zero vacuum expectation value, essentially picks some direction and orders. And then on top of that, you will have gold zone modes. Okay? And the Wess-Zumino term does very little in such a regime because it comes with a lot of derivatives, and it's a very high order term, so it's RG irrelevant in some sense. So the IR fate is just a bunch of gold zone mode. But it does, the Wess-Zumino term does do a little bit of stuff. What it does is to assign some non-trivial quantum numbers if you happen to have some topological defects associated with this order parameter. For example, if I have a vortex formed in the last two component, right? So if I have, let's say, N4, N5, these two component, so that's the valence-bond-solid order parameter. And if I have a vortex formed in this in the two-dimensional space, which is a point defect, then what this term does is to assign a spin half moment, essentially a 0 plus 1-dimensional Wess-Zumino term associated with this the first three components of this order parameter. So here in general at level k, that assigns a spin k over 2 to the vortex. And that actually agrees with the lattice intuition, because on the lattice, if I draw a vortex configuration associated with the VBS order, so this is the picture, okay? Then what happens is that you will see that there is always a single spin half moment at the vortex core that's not paired with anyone else. Right? So the vortex of VBS gives you a spin half moment, and that agrees with the Wess-Zumino-Witten intuition. But other than assigning things to topological defects, the Wess-Zumino term doesn't really do anything dynamically. Right? It doesn't really affect the gold zone mode, for example. So now let me say a little bit more about the weak coupling regime. So if I start from this gold zone phase and now turn on some terms that's allowed by my microscopic symmetries, the most important one is this term. It's a term proportional to n squared minus phi squared. Right? So in the SO5 language, this is one of the rank 2 symmetric traceless tensors. So if I look at this term, if mu is positive, right? First, even when mu is 0, the order parameter orders in some direction. It's just randomly choose one. Right? But when mu is positive, for example, it's energetically much favorable to choose to order in the phi component, in the last two component, than the first three component, in the Neel component. So what happens is at mu larger than 0, you get a VBS state, right, with phi ordered, but n not ordered. And vice versa, for mu negative, you get n order but phi disordered. Right? So in principle, just even with this Gaussian fixed point, you get a direct transition between a Neel and the valence-bond-solid phase, quite trivially. It looks like the Wess-Zumino-Witten term is not even doing anything there. However, this transition is a first-order one. It's in fact a strongly first-order one. It's, in the StatMat community, I think it's known as the spin-flop transition. Right? Essentially, the Gaussian fixed point is a little bit too boring to allow a actually continuous transition between these two. Okay. So basically, this weak coupling regime contains everything except the actually interesting fixed point. So to access the deconfined criticality, even in the pseudo-critical scenario, we need somehow to explore the strong coupling regime. And that's the hard part, right? Because first of all, it's not even strictly strictly speaking, it's not even well defined. The nonlinear sigma model in 3D is not really renormalizable. So we have to first even define what we mean by strong coupling regime, and then to explore whether there are interesting fixed points or even complex ones, and so on. So that has been the hard part for quite some time. I mean, people actually conceived of describing the deconfined criticality using this Wess-Zumino sigma model since, I don't know, 12, 14 years ago. But precisely for this reason, this model hasn't been as useful as, for example, the gauge theories like CPN models. So, okay, so strong coupling regime is hard to explore, but let's think about a much more familiar case, a much simpler case. So let's do everything in one lower dimension. Right? So SO5 in 3D is what we really want to study, but now let me think about SO4 Wess-Zumino-Witten model in 2 space-time dimension, right? So 1 + 1D. So this is the action. It looks pretty much the same as the one before, except I'm now in 2 dimension. Also, the order parameter no longer lives on S4, it lives on S3, which is the same as SU2. Okay. And again, pi 2 + 1, 2 meaning the space-time dimension, of S3 is again Z, right? So the Wess-Zumino term makes sense. This whole Lagrangian is well-defined. And what's better is that we know perfectly well the strong coupling dynamics of this Lagrangian. It's the well-studied Wess-Zumino-Witten model. Okay. So what happens is that if I think about this G, let's say, so I know that the weak coupling regime is actually unstable. This G = 0 fixed point is repulsive. That's essentially just Mermin-Wagner, right? Because in 2 space-time dimension, I'm not supposed to have a spontaneous symmetry breaking for this continuous SO4 symmetry group. Right? So if I'm at weak coupling, I should float to some strong coupling regime. But then there is an attractive fixed point at G = 1/k. Right? And this is the well-known SU2 level K Wess-Zumino-Witten CFT. And for K = 1, that describes the IR physics of the spin-half Heisenberg beta chain. So we know everything about this one. All right, so we know everything about SO4 in 2D. We want to know something about SO5 in 3D. Once I put it that way, it becomes very tempting to try to think about SO4 + epsilon or a target space S3 + epsilon in space-time dimension 2 + epsilon. Essentially, I try to interpolate between the SU2 level 1 story and the deconfined criticality story. Okay. So at epsilon = 0, that's the 2D SU2 Wess-Zumino-Witten, and at epsilon = 1 is the deconfined criticality I'm attempting to describe. Of course, if I want to think about Wess-Zumino-Witten physics, then this is a little bit weird because to define the Wess-Zumino-Witten term, I require some relation like this, right? Somehow I want this pi of 3 plus epsilon of this 3 plus epsilon dimensional sphere to be Z. I don't know what that means, except when epsilon is integer. Right? When epsilon is integer, this relation is always true. So for now, let me not actually define what I mean when epsilon is fractional. Let me just assume that it's well defined for integer epsilon, so let's just take analytic continuation of some sort. Right? What I'm really assuming is the existence of a nice analytic continuation from epsilon to equal to integer to general fractional epsilon, especially epsilon between 0 and 1. Okay? So this is the main assumption involved in this work. Okay? And it's an assumption. You can challenge it. I don't have too much to say beyond that it's assumption. But suppose I assume that, what do we expect? Okay? You can, this is a schematic RG diagram that I can draw. Right? At epsilon equal to 0, that's the SU2 level case story I just reminded you. Now let me think about epsilon slightly larger than 0. So first of all, the Gaussian fixed point will become attractive instead of repulsive. That's the same story as the standard nonlinear sigma model. Essentially, that's because as long as I'm in dimension larger than 2, the spontaneous symmetry breaking phase becomes stable. Right? It's possible to have that. That means somewhere here, I need another phase transition that happens, that separates the Gaussian fixed point and some other thing. This is, in the usual nonlinear sigma model, this will just be the, Ginsburg-Landau-Wilson-Fisher type of transition. But what's different from the usual, the standard sigma model is that I also have something here at coupling of order 1 or 1 over k. Right? So when I have a small but positive epsilon, I don't know exactly what's going to happen here. But as long as I assume some sort of analyticity, this fixed point should continue in some way. Right? If it just suddenly disappears, you'll have a hard time to actually make sense of this RG diagram. So let's assume that it continues in some way. Then at least for small epsilon, the RG diagram looks like this. You have attractive Gaussian, a repulsive fixed point here, and then an attractive fixed point here. But then it's also hard to imagine that this pattern will continue forever. Let's say if I'm at epsilon equal to 10 or something, right, at some very large space-time dimension, it becomes harder and harder to imagine that you can have a strongly interacting CFT this way. Right? I mean, it will be fantastic if we do, but it's just harder and harder to believe that it does happen. So a natural thing is that these two fixed points, one repulsive and one attractive, will collide at some epsilon. And above that critical epsilon, you no longer have fixed point at all. You just flow all the way to the Gaussian fixed point. Okay. So, basically with very little information, that's how much you can say already. But now you have roughly 3 scenarios, depending on where your actual physical dimension, let's say epsilon equal to 1, sits. There are basically 3 different possibilities. The first one is that your physical space-time dimension, let's say epsilon equal to 1, sits way above this merging epsilon star. Okay? And then doesn't matter where you start in the UV, you flow very quickly to the Gaussian fixed point. Remember, Gaussian fixed point is a first-order transition for the Neel VBS transition scenario, right? So that means in this case you just get a strongly first-order transition. Okay? So from numerics, that seems unlikely. Now the second possibility is that you sit here. So your space-time dimension is actually below this merging point. And then you get something very interesting. So if I start from strong coupling, then the system flows to an attractive fixed point. So this would be a continuous deconfined quantum phase transition. Right. Now, starting from this strong coupling fixed point, if I turn on that rank 2 anisotropy again, I'll get a continuous Neel VBS transition, right? If the appropriate terms are relevant. So this would be a dream that can fulfilled. And then there's the third possibility, which is my physical space-time dimension, meaning epsilon equal to 1, is just barely above this merging fixed point, right? So it still all the way flows to the Gaussian or first order regime, but near this G star, the flow is pretty slow, right? So the alpha I mentioned in the RG equation before will be something like proportional to 1 minus epsilon star. Okay. So essentially, I have this three scenarios, depending on where exactly epsilon star is. And the nice thing about this is that at least to leading order, this can be decided in a 1 over k expansion. So you can do some perturbation theory in 1 over k, which is by itself is not too surprising because we know that even for the 2D story, you can do a 1 over k expansion and calculate a bunch of stuff. So the beta function roughly looks like this. The thing is that it's controlled as long as both epsilon and g is of order 1 over k. Right? So if I have a very large k, then everything is small, things are controlled. And to leading order, the value of this G star and epsilon star looks like this. Indeed, they are of order 1 over k. But the funny thing here is that if you look at the expression of epsilon star, it's 0.77 over k. And now if I commit a sin that's very often being committed in the community, which is to do a leading order expansion in 1 over k and then plug in k equal to 1. If I do that, I know it's a sin, but suppose I do that anyway, then I conclude that the critical dimension is 2.77, which means the physical space-time dimension equal to 3 is barely above this merging point. Okay? And if I plug in everything I described, do some calculation, I conclude that it's a first order transition with a pretty large correlation length. Right? The correlation length is up to some order 1 factor, which depends on UV detail, about 400. Okay. So I should, of course, say that obviously this leading order calculation is not meant to be taken extremely seriously. It's suggestive at best, but so likewise, you can calculate things like scaling dimensions and so on. For example, if I calculate the scaling dimension of rank L traceless symmetric tensors of SO5, to leading order, I get some result like this, which means, for example, for the vector order parameter, which is like the Neel VBS order parameter, I get a number that's like 0.87. Compared with numerics, it's not that bad, actually. It's certainly better than what I expected before the calculation. The numerically, people get about 0.6. Well, for rank 2, it's less reasonable. You get something like 2.3, and the numerics is about 1. Also, you can calculate things like the drift of the scaling dimension. So if you measure scaling dimension at different system size, for example, L0 is the system size where you are closest to the complex fixed point. And if you measure the scaling dimension at different system size, it drifts roughly logarithmically as you increase the system size. And I should say this behavior is roughly consistent with numerics. I didn't put in a number from the numerics here because it's actually much harder to extract from the literature. That drift comes with a much larger uncertainty, but it's qualitatively on par. Okay?
Sorry,
So,
what do you mean when you say there's qualitative agreement? What's the measure by which you're assessing that agreement?
Actually, not very clear. So the thing I can say is they're of the same order, and they have the right trend. For example, this minus sign has the right trend. But other than that, it's
other than that, all the numbers are order 1.
Yes, yes. So the only thing Well, okay, there are a couple of things one can say. None of them will be very strong statement. And I don't expect to be able to say any strong statement. I mean, after all, this is a 1 over k calculation to leading order with k equal 1. But one thing is that, for example, you can try to do all this just in 2D, right? Just for the Wess-Zumino-Witten CFT, you can do a 1 over k calculation, take the leading order result for all the scaling dimensions. You'll get nonsense. Or things that barely make any sense, right? So to some extent, compared with that, this is doing already much better. So in some sense, it's suggesting that for whatever reason, this pseudo-critical point at 3 dimension seems to be less strongly coupled than the actual 2D Wess-Zumino-Witten CFT. So a 1 over k calculation seems to make a little bit more sense here than even there. Right? But beyond that, I can't say too much.
Question?
Yes.
So here you want to take k equals 1 because the 3D lattice model happens to have k equals 1?
Yes.
But could you engineer a lattice model with larger values of k to maybe check?
Yes. So, okay. Well, partly yes. So what happened is that there are lattice models that nominally correspond to higher k, but they are less useful because one special thing about k equal to 1 is that many of the other operators that I didn't talk about are RG irrelevant. Right? So, and those operators will be there on any lattice realization, at least on the lattice realizations that I'm aware of. So at k equal to 1, you don't worry about those things, for like rank 4 tensor and so on. But as you go to larger k, those terms, even at k equal to 2, you will have some term that becomes relevant. And then which means if you want to do this on the lattice, you want to look for some multi-critical point. And that's much more challenging for the numerical people. Right? But in principle, yes. In fact, for example, k equal to 2, nominally, you can think of it as the Neel-Babies transition, but for spin 1 moment per lattice site. Right? There, numerically, people see, I think, some sign of first order transition. That's fairly strong. But that's, even from this point of view, it's not very surprising because if you plug in numbers, you see that the rank 4 tensor seems to be relevant, and you seem to need further fine tuning. Yeah.
Can I ask a question?
Yes.
A couple of years ago, I think Zen B and co-workers tried to do a controlled calculation of this same RG flow where they introduced another parameter besides large K, and they seem to find evidence for this critical line that you drew.
Sorry, which critical line I drew? Sorry.
On the slide you're currently on, the line called critical.
Okay.
They seem to find that scenario.
That's possible. I guess I'm not familiar with that work, but my guess is that co-worker is in the audience. Tsenke, are you there?
Was he here? He maybe was before.
Oh, maybe he disappeared. He said he will snake out at some point. So.
Okay.
Yeah, yeah, I don't have much to comment about that work. Yeah, but okay, actually related to that, let me just say, yes, here, I meant to say this. So I don't want to claim, and obviously I shouldn't, that this 1 over k calculation is a proof of anything. It doesn't prove anything, right? For obvious reason. Right? It's a 1 over k expansion, leading order result, and I'm taking k equal to 1, which can be said for, most of the other epsilon expansion, 1 over n expansion, if I only have the perturbative result. Okay? So, and the result is suggestive at best. So what we really gain out of this is that it offers a picture, I'd say, to rationalize this scenario of critical points emerging, pseudo-critical behavior, and so on. And eventually, things have to be compared with what we quote unquote the experiments, which means Monte-Carlo simulations and so on. you need several different approaches to merge together to actually get the real picture.
Well, just one more comment about that. So they did work with a larger target space, as in your third point, and I think the idea of that was to truly bring their calculation under control. So I think it should probably
yeah. So I think their calculation, they let me see if I can remember. They involve some non-local kinetic term somewhere, right? That was
I think so. Yeah.
Yeah. Right. So before I end, let me say, make a few comments. So there are some, quite a few open questions that have not been answered. For example, I want a smooth interpolation between essentially SU2 level 1 and the deconfined criticality. But can I actually, do a better job at, sharply defining this theory at fractional dimension, especially when things seem to involve, the winding number of fractional dimension sphere on a fractional dimension space-time manifold. I don't know what that means. So can I do a better job there? The other thing is actually related to that maybe I can define things, just maybe, in the fractional dimension using some tricks from Bootstrap. And there have been 2 recent works on this direction. I think this one is closer to what I described a little bit. But I'd say those results from Bootstrap are rather primitive at this stage. They did see some sign of continuation, of dimensional continuation from the SU2 level 1 CFT to 2 plus epsilon dimension. And they did see that the kink, which might be a CFT, disappears around 2.7 dimension. But there seems to be some obvious issues with the numerics, and it's not clear if the numerical convergence was really there and so on. So there are multiple issues that still requires to be addressed before the final word can be said, or any serious word can be said. But it's certainly a direction that people are exploring and could explore further. Another thing related is that can we play the same game with different target space, right? So with sphere, we seem to get this diagram with probably epsilon star less than 1, but maybe with other target space, we can have different story, maybe even have a really interesting CFT in higher dimension. But that's speculative, we don't know. So with that, let me just summarize here, well, with these 2 figures, hopefully are self-explanatory, and thank you for your attention.
Okay, thanks, Chong, for the very nice and clear talk. And more questions?
I have one more question, just about the general idea of this complex fixed point.
Yep.
I would guess that even if such a complex fixed point is sitting near your theory, the true lattice model, its correlations all have constraints placed on them by the unitary of the original theory.
Oh, absolutely. Yes.
So
that's why
this complex fixed point must be of some limited use, right? Or
yeah. So the obvious limitation is you should work at system size below the correlation length. But as long as you're in that regime, then this complex thing is quite useful. Essentially, it controls your scaling behavior. Sorry, I'm trying to find the slide that I wanted to talk about. Yeah, for example, for the pulse model, you can just literally put it on a lattice and simulate it. And what you will see is that as long as, for example, for the 5 state, as long as your system size, your length is not larger than 2000, you see essentially everything predicted by the complex CFT. Actually, there are several quantities in the complex CFT that's we don't know how to actually observe them on the real in a unitary system, but a lot of them we do. Well, especially when things involve the real part of the central charge, the real part of the scaling dimension, and so on. Those things can be observed. The imaginary part that's harder. That some of those are involved in the drifting behavior, but some of those even more subtle.
Thanks.
I have the opposite question. So I would have thought if there's indeed a kind of near complex fixed point, it shouldn't change too much to both theoretical, so in particular theoretical prediction. So for example, bootstrap bounds are very constraining for regular CFTs. And if you have if you have a CFT that's in some sense very weakly complex, if that makes sense,
yeah,
the bounds completely go away as as they've been derived so far. But
yeah,
do you think it could be possible to still establish some kind of bounds, maybe slightly?
Oh, that I have no idea. That you need to ask some bootstrap guy. From my limited chats with them, it seems to be non-trivial to establish bounds of complex CFT in a controlled way. There's some less controlled version of bootstrap that may be able to handle complex CFT and may even have the hope of giving you something like this. But the problem is those schemes, my impression is they tend to be less controlled than the standard one.
Mm-hmm.
Okay. So I have a question about this complex fixed point.
Yeah.
So here you have complex fixed point at which you have complex scaling dimension, etc.
Yeah.
Right. This reminds me, maybe it's a far jump of thought, of the case where you have disorder and then you do some weird double epsilon expansion.
Yeah.
Punch disorder with double epsilon expansion, and then you get a real fixed point, but with complex scaling dimension.
Yeah, you're talking about this spiral
flow.
Yeah,
so,
yeah. So this complex fixed point, if you're really near the complex fixed point, you do get spiral flow.
Oh, I see.
It's only when you are on the real axis, the flow is unidirectional. I mean, the flow is straight. But as long as you are slightly off the real line, you get spirals.
And this drifting of scaling dimension, is that related to the spiral flow, or is that related to complex?
I think ultimately it's related to spiral. So if you can cook up a scenario where, well, essentially if you can cook up a scenario where what's in play is not the real and imaginary part of the parameter, but rather two actual parameter.
Right.
And somehow you can cook up the same, flow behavior, then you should see this bit more or less the same.
Oh, so I see. So you're saying that right here, it's the real and imaginary part that gives you the plane to have the spiral flow.
Yes.
In the disorder case, it's the disorder strength, and then
you actually have parameters that give you that. Yeah.
I see. I see. Okay, good. I have another question.
Yeah.
So is it possible to give up the SO5, instead you do SON, so that you have some other control parameter other than K?
Yeah, I think that's at least part of what Bijan and Tsenke tried. Sorry, what was I looking for? Yeah, so you can try other target space, for example. But the thing is, you can't directly generalize to, for example, SON and so on, because the topology won't work.
Right.
That's what makes it subtle.
To
generalize to higher N, you have to make some funny coset space and so on.
I see.
Yeah, but even just if you just do that, I think I'm pretty sure that you don't get a control in the perturbation theory. You have to do something else on top of that. I think what Bijan and Tsenke did was to modify the kinetic term in a way that involves another epsilon-like parameter.
Oh, I see.
Essentially introduce some non-local kinetic term and so on. So there is some small epsilon large n expansion that
I see.
they can do.
Okay, simply larger in itself is not.
Yeah, larger in itself doesn't do the job.
I see. Okay, thanks. Yeah.
I have a question.
Yeah.
So I think a couple of years ago, Engok-Moon, I think he did just brute force uncontrolled, I guess, RG articulation. So I don't remember his result, but is there any correspondence with what you conjectured?
I don't know his result, but I wouldn't be surprised if it looks totally different or otherwise, because the perturbation theories, the structure of the perturbation expansion actually looks very different if you directly do that. And for a somewhat detailed reason, essentially, yeah, okay. If I look at this term in the beta function, so this term actually comes from a, let me see. Yeah, this term comes from a standard one loop or two loop, depending on how you do it, diagram involving the Wess-Zumino-Witten term. If you directly do something like this in 3D, okay, let's just, for the sake of explanation, let's say in 2D, this involves a one loop diagram. And then in 3D, this involves a two loop diagram. So it's actually a different power in G.
Yeah, I know what you mean, because Wess-Zumino-Witten term has more legs.
Yes, so the structure of the perturbative expansion will be completely different. And I don't expect the results to.
I think I should check what he got, but perhaps he might have gotten fixed the point. I don't remember. It's totally. I think it's totally different structure.
Yeah. But I don't remember. I don't remember what he had actually. Yeah, I should look it up. Yeah.
Yeah. Thanks.
I have a question.
Yes.
I'm not sure I'm entitled to, since I'm a guest. So thanks for a nice talk. One aspect of your construction is kind of looks curious from one point of view. It's the fact that you have this SO symmetry group, and for many examples where we know how to analytically continue in the group parameters, we know that ON groups or SPN groups and so on, they come more naturally than SON groups, because for the cases when we know how to do analytic continuation, like the mathematical structure behind this, well, I did some work recently on this with Damon Binder, and there's some Deligne category, and those things, they exist for ON groups, but they don't actually seem to exist for SON groups, or at least they have not been constructed by mathematicians, and there's a real clear abstraction to their construction. So I was wondering, like, when you do the actual calculations, have you come up with rules of how to manipulate the epsilon tensor with non-integer number of indices? Because mathematicians haven't come up with.
Yeah, so good. I don't know how to do that. The reason I was able to show you this formula is because to calculate things to this order, I don't need that. It happens that to get things to this order with epsilon and g of order 1 over k, for the contribution to the beta function from the Wess-Zumino term, I only need the 2D result. I don't actually need the 2 plus epsilon d result. Now, if you ask me to do the next order calculation, I'll have to encounter things like that, like what you described, and I don't know how to do that. And that actually is in fact related to this point I said, to calculate everything to next order, even in principle, it seems I need a better definition of these things in fractional dimension. Sorry, I couldn't hear you. Are you on mute?
I'm sorry, I'm saying that if you actually manage to come up with some systematic definition of what you mean by SON with an integer n, it's going to be very, very interesting.
I see.
Because there's a real gap in the literature concerning this point.
I see. I wasn't aware of that. Thanks.
Any more questions? If there are no more questions for now, let's thank Chong again.
Thanks.
And Chong, maybe you can write your email in the chat. So
Oh, yeah. Sorry. You asked me to do that. I forgot. Let's see.
Yeah. If you want to talk to Chong one-on-one, or you can schedule a meeting with him. So he will be leaving his email in the.
Let me see. So. All right.
Okay. Well, thanks everyone, and thanks Chong. Thank you for the very clear talk. So yeah, if you have questions, you can contact Chong, and this meeting is recorded. So if you want to go back and replay it, you can. I think it will be on YouTube. Is that right, Sav? At some time.
Yeah. As soon, yeah. At some point, it will be privately on YouTube now, and eventually public once we sort out the media release information stuff.
Okay.
But yeah.
Okay, good. So thanks everyone. Hope to see you next week on Kadanoff Seminar.
Thanks. Bye.